All right. Well, thank you to our first of all top tier sponsor before we get started, Panasonic Ventilation. Make sure to check out Panasonic for all your ventilation needs. And very excited to mention that they are Green Innovation of the Year award winners from Green Builder magazine for 2019 for their Whisper Fresh Select Fresh Air Supply Fan. And also thanks to our main sponsor, Mitsubishi Electric, who are also Sustainability Award winners of the year for Green Innovative Product. Very excited. Panasonic, Mitsubishi provides all your heating, cooling, and filtration needs all in one. Today's low-load homes require right-size equipment that most systems, especially gas-fired, cannot meet. Mitsubishi has low-load, high-efficient heat pumps that dehumidify and cool in the summer and work in reverse to heat in the winter. Going ductless also reduces costs and can help you meet Energy Star and LEED goals. Ductless mini splits can now be hidden in many different ways to meet your client's needs, and ducted systems can be used as well. Here's just some examples of systems that can be retrofitted right in, hidden behind spaces, and not ruin the aesthetics of an area. Hyperheat ensures an efficient delivery system down to negative 13 degrees, which we never thought could happen anymore, but given last week's polar vortex, we know it does happen, and these systems are performing. Each room of a house can customize comfort while still being all electric and energy efficient for the clients with different needs, and only heat and cool rooms as needed. Multifamily and commercial centralized variable refrigerant flow or VRF systems work great on larger projects looking to serve whole buildings. And VRF heat recovery technology permits simultaneous cooling and heating. As this illustration depicts, only certain areas in the red are being heated, and others are cool as needed as the sun moves around. So check out Mitsubishi Comfort today for all your electric HVAC needs. All right, so welcome to How to Improve Indoor Air Quality to Comply with LEED and state ventilation codes. This course is approved for 1 hour in continuing education units, LEED AP Homes, GBCI, NARI Green, AIBD, BPI NonWholeHouse, as well as AIA Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. Today, I'll be your moderator. My name is Brett Little, and I am the executive director here at the nonprofit, the GreenHome Institute. So what we're seeing is that codes, most of this country is on on an energy code, but we're going beyond energy codes and we're getting into ventilation codes and in many cases getting into green codes. So what are some easy ways to gear up for those codes as they're coming or when they're adopted to be able to meet them and help improve your clients' projects? And so that's why I'm excited to have our speaker here today. In the late 1990s and early 2000s, Jeff managed many different utility programs, supervising a staff of over 30 in making existing homes more energy efficient and comfortable to live in. In addition, for the past 20 years, Jeff has worked with builders to design residential ventilation systems and select the right products and train installers on proper sizing and installation to ensure better indoor air quality and a healthier lived-in environment. He is certified in the residential ventilation installation by the Canadian Mortgage Housing Corporation, and in 2003 became certified as a HERS rater. In his current role as a National Indoor Air Quality Manager for Panasonic Eco Solutions, Jeff leads a team of IAQ specialists across the country who strive to help builders build durable homes with healthy IAQ. All right, so with that, Jeff, please take it away.
All right, so let's go ahead and get started. We have a lot of information to cover today. Thank you, Brett, for the nice introduction. Let's just run through the objectives here quick before we get started so everybody knows where we're going. We're going to discuss the contributing factors to poor indoor air quality. We're going to explain the impact of poor indoor air quality on our bodies. We're going to show how moisture damages homes and contributes to poor indoor air quality by showing how moisture is created and how water vapor moves throughout the house. We're also going to discuss ventilation codes and calculations and how to get to the right ventilation rates to meet either program requirements for LEED or the requirements for the Michigan and Ohio, and as well as other states' building codes. And then finally, we're going to review 3 ventilation strategies: supply, exhaust, and balanced. And I'll talk a little bit about the cost of each of those systems and some of the impact that homeowners can have on them. So with that said, we'll start off with a little slide here. Albert Einstein once said that if he had 20 days to solve a problem, he would take 19 days to define it. Well, we don't have 19 days today, but we're going to spend quite a bit of time today defining what is good indoor quality and what can have negative impacts on that. So I'd like to start off with a couple of questions for the audience. First one is, would you be comfortable breathing the air from your partner's mouth? Would you be comfortable with this child breathing the air coming out of its mother's mouth? And certainly most of us would say, no, I'm not comfortable with a smoking mother blowing smoke in her child's face. Would you be comfortable breathing the air coming out of your dog's mouth? Or worse yet, would you be comfortable with the air coming out of this end of the dog? And then in addition to that, we also have pet dander that goes with our pets as well. So, our first impulse is to turn away. After all, if we can't see it, it can't hurt us, right? But what about the pollutants that this little critter is adding to our households if they're in there? And then garbage disposals and sinks and all kinds of other opportunities for indoor air quality to be negatively impacted. So we say yuck, but with the homes that we're building these days being tighter and tighter, we have to take into consideration the activities that are going on in the home and how those activities are impacting indoor air quality. In defining it a little bit further here, healthy air can best be described as air that's fresh at a comfortable temperature and humidity and free of chemicals, mold, and other contaminants. There are many ways to improve indoor air quality, and doing so not only makes a living space more comfortable, but saves energy, money, and improves the health of the occupants. So that's how we want to define it. The first step in ensuring healthy indoor air quality is recognizing what can compromise it, and we're going to spend a lot of time talking about that. Excess contaminants and moisture have the largest impact on indoor air quality, but even air that is too dry, cold, or hot can lead to discomfort and health problems. So, many of you have probably seen ads recently on TV for Febreze, where mom walks into the young man's bedroom and makes the stink face because it smells like a locker room in there. But the young man and his friend playing video games don't smell the odor because they've been sitting in there. And that's, and they use the term nose blind, and that certainly happens to all of us. We leave our home, go out shopping, come back for a couple of hours, and we come back in and we can smell odors that we couldn't smell when we left. So your olfactory senses, or your sense of smell, are the first sense, it's the first one that you lose sensitivity to. So it is in fact a reality that there are many things in our homes that we cannot smell. Having said that, where does all the stink and moisture go when a house is built tight and we can no longer smell or see it? It's not leaving the house, but it's still there. So, and again, it's because we're building these homes tighter than we did 30 years ago. So what these smells, bacteria, viruses, VOCs do is diffuse. They want to reach equilibrium. So they diffuse to the point where our senses no longer recognize them, though the impact those pollutants can have on our bodies remains. There's a lot of information on this slide, and some of it really jumps off the page to me. Pediatric asthma rates have jumped 72%. The next one really, and I think we can all identify with, and this study was done with women, but I would imagine the impact is similar on men and children as well. Women who work in the home have a 54% higher death rate from cancer than women who work outside the home. And when you think about, you know, our ventilation codes in commercial buildings versus residential building, you know, I don't know that this can all be contributed to ventilation code, but certainly it's probably having an impact, you know, on these numbers. The EPA has stated that air quality indoors has been found to be 70% more polluted than outdoor air. You know, sick building syndrome, we've heard of, you know, some of these things, and certainly, you know, they reside in our homes as well. And when I read that one, I thought about a little bit about the people in Flint, Michigan with the drinking water, you know, problems. And I think homeowners probably assume that the air in their homes are healthy to breathe, but in fact, you know, 87% of them had never had the air quality in their home checked, and they have no idea if it's healthy or not. And when you combine some of these, you know, numbers with the final one there, that we spend 90% of our time indoors, and then go back up to the fact that it could be 70% more polluted than outdoor air, you know, really has an impact on our health. And we don't normally think of moisture as a pollutant, but certainly moisture, especially in its liquid form, can cause damage to buildings and certainly can impact indoor air quality as well. So we're going to spend some time talking quite a bit today about moisture and how it moves through the home. And did you know that as humans, we off-gas 1% of our body weight in 8 hours of sleep? So if a 100-pound person over a 24-hour period, if they're exhaling a pound of water into the air, that's one individual that's adding 3 pounds of water to the air in a day. And you know, again, we have our plants and our pets also dumping moisture into the air in the home, as well as cooking and showering and other activities that add moisture load to the home. So, and here's some of the sources. You know, the dishwasher, certainly our pets, our showers, our cooking, our laundry. All of these things add moisture to the home in the form of vapor. And where does that moisture end up? You know, moisture requires a certain amount of temperature to stay aerosolized as a liquid in the air, as a lighter than air gas. And when the temperature is reduced, the moisture changes phase and becomes liquid, and that's where we run into problems. Since air holds very little temperature mass, the changes of phase that typically occurs on a surface. You know, if you're living in the northern part of the country, certainly you're familiar with that recently on your windows. Even very good windows will have some condensation, you know, with the extreme temperatures that we've had of late with the polar vortex. And it's going to condense out as water on these colder surfaces. And oftentimes that can be, you know, an exterior wall. So let's talk a little bit about that moisture in the air. This table shows on the left temperature, on the top relative humidity, and on the bottom absolute humidity. So absolute humidity is the amount of moisture in the air. And on this slide here, let's take an example now of 68-degree air and follow that line over from the left to the line where we have 1/100th of a gram of moisture in the air aerosolized. And then follow that curved line coming off of that corner up to the top, and it shows that we're at 70% relative humidity in this situation. So now let's take that same air and drop the temperature down 11 degrees and take a look at what happens to the moisture in the air. Now we follow that 57-degree line across over to the same 1/100th of a gram of water in the air, and then follow that curved line up to the top, and we realize now that the relative humidity is at 100%, and something's going to happen. That air is going to find a cold surface, and it's going to come out of the air in the form of liquid, whether it's rain or it's condensation on a cold surface. Now let's take that thought and move it indoors into our home. Here we have a pot of water boiling on the stove, and as we discussed earlier, that vapor is going to try and reach equilibrium, so it's going to spread throughout the home. And now looking at the thermal image on the right, we see that in the foreground, the bright yellow, we have a floor surface that's at 69 degrees. But in the back corner and outside corner, we have a corner that's at 58 degrees. So with our temperature drop moving from the interior of the home to the exterior on the outside walls, we're going to have a problem when that moist air is cooled and its carrying capacity for water is reduced, and we're going to have our own little chia pet growing in the corner. And this is, of course, something that we want to avoid because we've got mold spores in the air, further degrading our indoor air quality. So let's talk just briefly about 3 principles of physics that can in fact impact the building science. First, we know that hot moves to cold, wet moves to dry, and high pressure moves to low pressure. And all of these things are trying to equalize, right? Spread out and become the same throughout the home. By adding heat to water, it vaporizes and turns into a gas. And we've all seen this many, many times in our life with popcorn. Did you know that when water expands, it expands at the rate of 1,500 to 1 from liquid to vapor, and that's what causes the popcorn kernel to pop. When the moisture, or when the liquid in the kernel turns to vapor, it pops the corn, it cracks the shell, and becomes vapor. So, and as we discussed before, water can move, faster as a vapor than as a liquid. So back to our thermal image here. By removing heat, vapor can condense back into a liquid and things begin to grow. So, where we're creating moisture, either on the stovetop, in the shower, through respiration, that moisture is in the air and it's going to travel and equalize throughout the home. And if it comes in contact with surfaces cold enough to reach cold enough so that it's going to reach 100% relative humidity, that's where we're going to have problems like this. And in the summertime, as a previous slide had said, it can happen on air conditioning vents. So there's 2 ways, 2 strategies for dealing with excess moisture. One is to heat or warm the condensing surface, so trying to warm up this corner, which, as we've discussed, with the temperatures in the upper Midwest the last few weeks, trying to warm an exterior corner, warm enough so that it's not going to create problems like this, can be a real challenge. If it's minus 20 degrees out, which we've had, I'm sitting here in beautiful Green Bay, Wisconsin today with 2 inches of fresh snow on the ground, and it's about 25 degrees out here today. But a couple of weeks ago, we had minus 20 degree temperatures, and warming those outside corners especially is very difficult. So the other option that we have is to remove the moisture from the air and replace it with dry air via ventilation. So in defining the problem further here, in most cases, healthy indoor air quality begins with and relies on the exchange of indoor air and outdoor air. Outdoor air is generally cleaner, as we discussed with the stats that I showed, where the EPA shows that indoor air can be 70% more polluted. However, certain conditions can worsen outdoor air quality, and certainly the California fires comes to mind. If you're pulling outdoor air in to improve your air quality in an area where there's a fire, you may not necessarily be improving the air quality, you might actually be degrading it. So in those conditions, making sure that poor outdoor air is tempered and filtered before it enters the home is an important proactive step to ensuring healthy indoor air quality. And there's a whole host of chemicals that we store in our homes and in our garages. And, you know, if you don't know it already, there's a lot of communication between the garage and the home, and whatever you're storing in your garage, those VOCs from those chemicals, whether it's gasoline or fertilizer or pesticides, those chemicals can often end up infiltrating into your home as well. So, and then there's a whole host of chemicals that we store, you know, in the home, under the sinks, in the basement, paints, you know, what have you. And those chemicals, or those products, are also off-gassing into the home, not to mention the building materials. So once it's indoors, the buildup of contaminants and moisture is the greatest threat to indoor air quality. Knowing which substances and activities can contaminate indoor air quality and avoiding them when possible is a great proactive strategy. However, contaminants come in many forms and originate from a wide range of sources, so it can be nearly impossible to prevent all of them from infiltrating the home and affecting your indoor air quality. So we have two ways of dealing with these pollutants. You know, there are proactive strategies and reactive strategies. Preventing the introduction of chemicals, moisture, and undesirable conditions, temperature gains or losses is a proactive strategy, and a reactive strategy is removing the contaminants if they have been introduced. So we can either remove the source by taking those products that are off-gassing into our homes out and storing them maybe in a shed or something like that, or taking them out of our attached garage and putting them into a shed, or we can reactively try to remove them with ventilation. And another proactive strategy, as we discussed with the fires, would be to filter and heat the incoming air, or cool it during the summer, and you know, conditioning that air before it's brought inside the building envelope. And then a reactive strategy, as we discussed, would be to get rid of the odors, get rid of the chemicals, the VOCs, by removing them and replacing the bad air with good air. Okay, so now we've covered a good portion of what's going to impact the air, whether it's actual VOCs or moisture. So let's switch gears here now and talk a little bit about how to calculate the correct amount of ventilation for the different programs. In Ohio, starting July 1st, I think this was voted on back in November, and as of July 1st, you will have some new building codes in the state of Ohio. The first one there, section 303.4, is going to require mechanical ventilation in dwellings with air changes of 5 air changes or less, and that's going to be based on a blower door test. And if your reaction is to say, well, then I just won't build a home, I'll build a leakier home so that it doesn't get below 5 air changes an hour, there's another new code that says that buildings shall be tested and verified as having an air leakage of not more than 5 air changes an hour. So can't get away with that strategy, and we wouldn't want to anyway, because homeowners nowadays will not accept a leaky home and the discomfort of a drafty home. So, and then the last, well, not the last one, but the next one reads that whole house mechanical ventilation systems shall provide outdoor air at a continuous rate in accordance with the table 1505.4.3 or equivalent total based on this calculation, and we're going to go into both of these a little bit more here in a minute. This is a chart right out of the Michigan code book, and in Michigan, like Ohio, there's a ventilation code. The states have, and all states approach it differently. What Michigan has chosen to do is take the easy route, and I have no problem with doing this because it eliminates any questions, and that is by just taking the square footage of the home and the number of bedrooms, and making sure that the home is ventilated at a continuous rate to meet the specification of this chart. So because we're going to use a 2,600 square foot home in our calculations on future slides, let's use that for this chart in Michigan here. And the same chart applies in Ohio as well. So our 2,600 square foot home, we follow that across. It's between 1,500 and 3,000 square feet. 4 bedrooms is the number that we're going to use for our calculations. So using this chart, we see that a home in Michigan or Ohio, using the chart, would require 75 CFM of continuous ventilation. So now let's take a look at the calculations using our 2,600 square foot home. And I'll first mention, you see the term ASHRAE there, ASHRAE, which is the American Society of Heating, Refrigerating, and Air Conditioning Engineers. In your code books, you're not going to see the codes referred to as ASHRAE 62.2, 2010 or 2013 version, but understand that ASHRAE is a third-party entity that determines the correct or determines the ventilation rates, and states just use an extract of the ASHRAE code and supplant them into their codes, although they will not refer to ASHRAE 62.2 in the code books. So on the left-hand side of the page here, you see the ASHRAE 62.2 2010 calculation. Again, we're using our 2,600 square foot home, 4 bedrooms, and in that calculation, and what applies in the state of Ohio, is the number of bedrooms plus 1, number of bedrooms plus 1 times 7.5 CFM plus a 1% calculation for the square footage of the home. So using the 2010 calculation, we would require 63.5 CFM of continuous ventilation. Now, we can't go below that number, but I do believe most codes allow for a 10% upside to that. And in fact, if you go back and look at the chart that we looked at before, clearly using that chart is higher than the 63.5 CFM, and that the states allow for, and ASHRAE allows for, up to 10% over the code, because it's really, nearly impossible to dial it in exactly to 63.5 CFM. Now, on the 2013 version of the ASHRAE 62.2 code, you'll see that there is a little bit of a difference in the calculation. The number of bedrooms plus 1 times 7.5 is the same, and that portion of the calculation is really focused on the number of occupants in a home. We're going to assume 1 person in each bedroom, and the plus 1 addresses the master bedroom, where there's an assumption that there will be 2 people in that room. So we take the number of bedrooms plus 1 for that extra person in the master bedroom, times that times 7.5 CFM, and then in this 2013 version of the code, we see that it's now a 3% calculation for the square footage of the home. And that raises the ventilation rate, the continuous ventilation rate, all the way up to 115.5 CFM, again, with the ability to go over by 10%. I don't know that for sure for the Ohio code, but that's what most codes would allow, is up to 10% overage. So now we know what
Jeff,
these new codes are. Yes.
Yeah, and if you want to go back to that slide, I wanted to reiterate real quick that for the LEED BD and C version 4 certification, it does comply with ASHRAE 62.2 2010 and not 2013 under section 5 and 7. So I just wanted to make sure that was clear, both for this version of V4, and I believe the newer one coming out should still continue to comply with 2010.
Perfect. Well, then I learned something today too. That's good. Thank you. All right. So now that we know what the codes are and how to meet the codes in terms of calculations, let's talk a little bit about some of the systems that we can use to meet the codes. tightly built homes require predictable and uneventful ventilation. Now that's a really important point, predictable and uneventful. The reason we're introducing ventilation codes is we can no longer rely on homeowner interaction to ventilate our homes. Just simply turning on and off a bath fan is no longer, or a range hood fan is no longer acceptable under the codes, because oftentimes, it's not enough ventilation. So we want to have predictable and uneventful ventilation at the rates specified by the code. And there's three strategies for getting there. First one would be an exhaust-only strategy, and I'm going to talk a little bit more about the pluses and minuses of each of these, but note that as we go down the list here, the cost as well as the homeowner interaction with these systems increases with each of them. So we have an exhaust-only strategy, we have a supply-only strategy, and we have a balanced strategy. So on the exhaust-only strategy, what we're doing here is we're basically just upgrading a bath fan from, maybe an old AC fan that's on a switch to a higher efficiency DC motor product that was going to run continuously. And usually the ventilation codes will specify that the exhaust ventilation strategy as well as the supply ventilation strategy will require a DC motor for energy efficiency reasons. So basically all we're doing here is upgrading from an existing AC on-off ventilation in the bathroom or somewhere else in the house to a DC motor product for energy efficiency purposes. And we're relying on building shell leakage or infiltration to make up the fresh air or to supply the fresh air to the home that the exhaust fan is taking out. And this creates a little bit of negative pressure in the home by exhausting the air so that the building shell leakage will allow the fresh air to leak in. Now, oftentimes when I talk with builders, they will say, well, we build our homes so tight that, we can't rely on exhaust ventilation and building shell leakage to make up that fresh air. And my response to them often is, does the clothes dryer work? Because the clothes dryer is running at 200 to 250 CFM. And if the clothes dryer is drying the clothes, it's drawing air through the building shell at a rate much higher than a 73.5 CFM bath fan might. So I think most of the homes in the country are going to leak enough to allow for 60 to 100 CFM of building shell leakage to supply fresh air for an exhaust-only strategy. And these are good strategies the further north you go in the country, because that building shell leakage can actually have somewhat of a drying effect and dry out some of those moisture issues that we might have talked about, or that we talked about earlier in the slides. So that's the exhaust-only strategy. So let's talk a little bit about supply strategy, and that's basically the opposite of the exhaust, where now we're going to force air into the home with a fan, and this is often done with the furnace motor and a duct connected to the cold air return on the furnace with a damper to open and close when the ventilation system is run. And then there's a control put on the furnace telling it to run the blower motor X number of minutes per hour to pull air in. The damper opens, the motor kicks on the furnace, and it draws air into the negative or the return air side of the furnace, forcing air into the home. In this case, we're relying on building shell leakage to exhaust the stale air out of the home. So we're pulling the fresh air in through the furnace, through the cold air return. One of the pluses of this design is that as it's being pulled in by the furnace motor, it's also being filtered as it's going through the furnace before it's distributed throughout the home. So that's one of the pluses. This may not be the ideal ventilation system for northern climates because, as we discussed earlier, if this home is in a northern climate and it's 0 degrees outside, and the air that's being forced out of the home through the building shell is, let's say, 62 degrees at 35% relative humidity, I think we all know what's going to happen when that warm, relatively moist air is being pushed out through the building assembly and hits the cold 0-degree sheathing on the outside. Now we're going to have just exactly what we talked about in some of the earlier slides, where that warm, moist air, its carrying capacity for the moisture is going to exceed, it's going to exceed the air's ability to carry that moisture, and it's going to condense out on those building materials as it's exiting the building and creating a wetting issue and some of the issues that we talked about in terms of durability. Some of the other problems, well, first of all, this is also a little bit more expensive than the exhaust only, because with the exhaust only, again, we're just upgrading a bath fan. With this strategy, we're adding a damper, a duct running to the cold air return, and a controller on the furnace to make it run, again, the specified number of minutes per hour needed to meet the ventilation rate. So this strategy is probably better for warmer climates, warm, humid climates, than, say, an exhaust-only strategy. So we have to think about where we're building the building if we're using, depending on which strategy we're using. So exhaust ventilation might not be the best ventilation for Houston or Miami, and supply ventilation may not be the best strategy for Fargo, North Dakota, or Green Bay, Wisconsin. And there's another expense associated with this strategy above what the exhaust strategy is, and that's operating cost. So instead of running a small DC motor bathroom fan at, say, 6 to 10 watts, now we're running a furnace motor to operate the ventilation system. So it's a bigger cost. Again, it's probably specified in the code that furnace motor be a DC motor, but there is additional operating cost with this system as well. And we're relying on the homeowners to make sure that the intake on the outside of the home is not plugged, that, when Junior's cutting the lawn out in the backyard and he's blowing the grass clippings towards the side of the home, that we're not plugging up that intake. So that's the pros and cons and costs associated with the supply strategy. So balanced, many building science people, and I don't disagree with them, that balanced ventilation is probably the best strategy throughout the country. But it too has pluses and minuses. One of the biggest minuses is the significant additional cost. And I'm not bad-mouthing HRVs and ERVs. Panasonic makes ERVs, so and we can continue to add to that portion of our product line. But there is a significant increase in cost when you go from supply or exhaust to a balanced system, because you're adding more ductwork. The equipment itself is significantly more expensive. And then we have those additional operating costs as well, not just the operation of the equipment itself, but oftentimes this type of equipment is tied in with the furnace blower that I mentioned, along with the supply strategy, and it's using the existing ductwork and the furnace motor to distribute the fresh air that an HRV or ERV is bringing into the home. So there's operating cost increase. There's also, again, the significant increase to the cost of installation and purchase of the equipment. The pluses to balanced ventilation are that now we no longer have the negative pressure that's created by the exhaust strategy and the fresh air being dragged through the building shell. We no longer have the positive pressure created in the home by the supply strategy that's allowing air to leak out that's requiring air to leak out through the building shell. We are bringing air in and out of the home through ducts in a balanced fashion. So we no longer have that positive or negative impact on the building. And we have control of exactly where that air is coming in, and we can filter it and temper it. In fact, the HRVs and ERVs have a heat recovery energy core in them. So they recover some of the energy, whether it's the heat that's being exhausted, during the wintertime, or some of the cool air that is being exhausted, and it's cooling down some of the incoming air during the summertime that might be drawn in to replace the cool, stale air. So there are pluses and minuses to all of these systems. And again, many people will say that balanced ventilation is the best strategy across the country. I don't disagree with that. My concern with this strategy is it requires a whole lot more homeowner interaction and education. We struggle to get many homeowners to change their furnace filter. With the balanced strategy, now we have to rely on the homeowner to open the cabinet 3-4 times a year, clean it out, clean the filters, and once a year take the core out and clean that off as well. And then they have to go outside and make sure that the intake and exhaust vents, the supply and exhaust air vents are clear as well. So I would say this is a great ventilation strategy in houses where it's affordable, and also where we have homeowners who are going to be able to do the maintenance required, because I've been in many homes where HRVs and ERVs are only a year old and they are completely inoperable, because either in one case we found the manual sitting over the core, so there was no heat exchange going on. The vents on the outside of the home are often plugged, or we open them up and they're full of Eurasian lady beetles or some other insects. So again, in the right home, great system, but I think there are some significant homeowner education and maintenance issues to overcome with this strategy. Okay, and then finally, we can have the best ventilation system in the world, the best equipment, but if it's not installed properly, it is not going to operate. And we have to talk a little bit about static pressure and its impact on ventilation equipment. You can wire a fan and run the wire from one end of the house and back, and when you flip the switch, power is going to come out the end. But when we run ducts all over the place, with elbows and dips and sags, it's going to have an impact that increases static pressure, and it's going to significantly impact the performance of ventilation equipment. So we have to be very aware of how many elbows, dips, sags, and the type of material that we're making our duct runs with. And it's very important that it be installed properly. And ventilation equipment it's a very tough install, because there's so many hands that touch it. You have an electrician that wires it, an HVAC contractor who does the duct work, and then a siding contractor who puts the termination on. So you've got potentially 3 different contractors touching that piece of equipment and impacting its performance. So that's a struggle, I think, for builders, and we have to keep that in mind, that every step has to be done right, or the equipment will not operate properly. Roofing is put on by a roofer and flooring is put in by a flooring guy, but with ventilation equipment, there can be as many as 3 contractors touching the stuff before the air can make it to the outside of the building. And how we terminate, not only the duct run, but the terminations can have a big impact as well. So here we have 2 different soffit terminations, and soffits are a great way to terminate a bathroom fan because it's generally a straight shot down between the trusses and over the top plate and out. But if we do a great job installing the fan and installing the duct work, and we put a termination on that chokes the snot out of the thing, it still is going to fail. So we have to make sure that the termination, and the top picture here is a product that comes with, and the grill is the insect screen is pulled off of here, but the insect screen on this one is so fine that it offers a great deal of resistance to that fan before the air can make it out of the home, as opposed to the product on the bottom, which is an HVI certified product. that offers very little resistance to a fan. So we have to make sure that we're installing the equipment properly for it to perform properly. Now, I want to give you a little hope before we wrap up. and here's the hope that I have for you. If your resistance to the codes is that homeowners are not willing to pay the cost of improving their indoor air quality, Dodge Data and Analytics did a study and in fact showed that 83% of homeowners are willing to spend more money to have a healthy home. And then in the bottom right-hand corner here is some comparison between what realtors have found about homeowners and what they're willing to spend or what they would like. And a comfortable living space outranks new windows or lower utility bills. So occupants and homeowners and builders are willing to spend a little bit of money to have good indoor air quality. So let's review what we've covered today. By now we should know that we're building tighter homes. We certainly know that. That's the whole reason for introducing the ventilation. We know contaminants will be present. We know how these contaminants will move through the home. We know they will damage the home and the health of the occupants if they're not dealt with. We know how to determine the proper ventilation rate and how to calculate that rate if we have to. And we know 3 different strategies of ventilation to meet those codes, as well as a little bit about proper installation. So with that, I thank you. My email contact information is there if you need it. And thank you all very much. And I'm open to some questions.
Hey, thanks, Jeff. Yeah, we definitely got some questions pouring in here right now as we speak. And right before we get to those questions, let me go over just one thing real quick. All right, so I want to say a huge thanks to all of you for joining us. Thanks to our board of directors, thanks to our volunteers, thanks to all of our members, and a huge thanks to our top tier sponsors who allow us to do what we do. Shrinergy for on the go or in your house or office backup solar power battery systems that work to help keep things moving, not if, but when the grid goes down. T-Stud, structurally insulated framing systems that save money behind the walls and are easy to build right in, insulated studs. And then Mitsubishi Electric to help you get to net zero, going all electric heat pump systems that work even in the coldest of cold temperatures. All right, so with that, Jeff, one of the questions I see right now is, does the Ohio Table 1507 3.3 airflow chart require the same amount of ventilation regardless of blower door tested building tightness? Does it assume that the building meets the code but does not exceed the tightness in terms of tightness rather?
So I would say that that's something that you want to ask your local building code official. My understanding is the way the codes read is that every home in the state of Ohio after July 1st will require a blower door test. It will be required to test out at less than 5 air changes an hour, and therefore it will be required to meet the ventilation code. But again, check with your local building code official, excuse me.
Great. And the next question is, does pressurized corridors less than 0.5 CFM per square foot ventilation strategy in multifamily building work with exhaust ventilation strategies? Since the corridor in baseline only requires 0.06 CFM at square foot ventilation, supplying over 0.5 CFM square foot ventilation caused a huge cost penalty.
So that's going to be, I think, covered by ASHRAE 62.2.1, which is the commercial ventilation code, which we did not cover here. And I am very much less familiar with commercial codes than I am with residential codes. And I think that ASHRAE 622.1 starts at 4 units or more. So this is only, the codes we discussed today would not apply to that question, and it's a more technical question than I'm able to answer in the scope of this discussion.
So I guess, Jeff, would there be a way that somebody that you could find, or have them contact you and then maybe help them find an answer?
Yeah, in fact, actually, if you go on and look up Ohio Buildings and Standards, the codes are there, and there's a gentleman, I think his name is Jason, and there's a phone number, and you could call and ask him those questions, and he would certainly be able to answer them as the state code official.
And I assume that could apply to any state. I don't know if this was specific to Ohio or not. So.
Right.
Okay. So the next question is, do you have any information as to the effect on indoor air quality of HVAC makeup air? They have passive vents installed, no fan, but do allow fresh air in from the outside. HVAC contractors have sketchy understandings of why they install these as required by code.
So are we talking about the cold air return supply, the fresh air supply through the cold air return? Is that what this question is regard to?
I'm going to say yes, but to the attendee who asked that, feel free to follow up. Yes, that's a yes. Yep. Okay.
So there's been, testing done, and the cold air supply or the fresh air supply system through the cold air return with the damper and the timer on the has been a struggle for a number of years because of a number of different reasons. First of all, it's very difficult to test how much air is actually being drawn in with the damper open and the furnace blower running. I know that years back we did a study like that in Wisconsin, and we found that where that duct from the outside is attached to the cold air return has a significant impact on the amount of air being drawn in. If you are outside of where returns are coming in from the home, your negative pressure in the cold air return is going to be significantly less than if it's right on the furnace drop, for example. And so we really, it's very difficult to test the air being supplied. You could measure from the outside by putting a hood over the intake, but it would have to perfectly match up with the siding or, the portion of the foundation that the duct is running through. So it's very difficult to measure. And in the testing that was done with airflow grids inserted into that supply, I think some of the highest numbers came back at like 30 CFM. So when tested, that system has not always met the requirements, but it's very difficult to test, and I think in most cases it is not tested versus an exhaust fan where you can throw a hood over it and test it, or the cumulative supply and returns of a valence system.
So keeping on that note, I do know that there are other ways to ventilate balance-wise besides an ERV or HRV. And in fact, arguably, if you're talking about, being really tight with your dollars and trying to get to net zero, there are many arguments out there being played out that you still need to do balanced, but that maybe an HRV or ERV is not the best place to spend your money. So in that case, could you talk a little bit about any kind of strategies someone could use to still hit balanced, but not necessarily have to do the upcharge of an HRV or ERV?
Absolutely. The calculations on the amount of heat recovered with an HRV and ERV, and again, I'm not bad-mouthing HRVs and ERVs because Panasonic does make and sell them, but the calculation on how long the payback is on that equipment based on the energy savings, the payback is out there a long ways. So I think that is supported by what you're saying, Brad. And I didn't want to talk about Panasonic product during the presentation, but yes, certainly, Panasonic has products where you can run a DC motor exhaust fan that is drawing air out of the home and having that same duct return or duct going to the return side of the furnace and opening that damper to alleviate negative pressure in the home, or even engaging the furnace blower. So now you have, what we would call, what Panasonic calls our select cycler system, that is running a bath fan at the same time the blower motor is running and sucking air into the home. You're exhausting air from the home at the same time. There's no heat recovery, but it is a balanced system in that regard.
Can that work on renovations too?
A little bit more difficult with renovations because you do have to run some low voltage wires to tie the system together. We are working on solutions to make that wireless, however.
And then I do appreciate someone chiming in here. I want to quick reiterate that for pursuit of LEED, and honestly just the best strategy if you do have multifamily, you do not want to be pulling that ventilation out of the corridor. It does need to come from outside if you are doing exhaust only. So I appreciate the attendee speaking up about that and making that apparent. As far as LEED pursuit goes and just best practices, you do want to avoid that. So anyway, the other question is, could you repeat which strategy, exhaust or supply fans, is the best for hot, moist climate and those for cold northern climates?
Sure. For a cold northern climate, and it doesn't have to be just a cold northern climate. Let me address it in reverse order. So I would say that a balanced ventilation system is good for any climate. In hot, humid climates, such as Houston or Miami or probably most of Florida, the supply strategy is probably the best strategy. Anywhere from there north, anytime there's a dry climate, because it's the least cost, both in terms of upfront cost and operating cost, the exhaust strategy is probably the best strategy for 90% of the country.
Okay, great, thanks. And I'm going to paste in the chat here the link to the quiz, or sorry, survey, not the quiz. The quiz is for those watching on demand, but make sure to take that survey. I'm going to post that here in 1 second, and then it looks like we have one last question before we wrap up, and that is, do you recommend air exhaust fan or supply fan for climates with high winter moisture and temperatures of 30 to 68 degrees Fahrenheit with a little sunlight?
Ask a question back, and that is, are we talking about the Northwest? So repeat the requirements.
So the question is, do you recommend an air exhaust fan or supply fan for a climate with a high winter moisture and temperatures that seem to range between 30 to 68 degrees Fahrenheit with little sunlight involved?
Okay, yeah, I'm going to guess that that's a Northwest question. I would say, when you're doing supply, or in either case, when you're extracting air from the building and you're drawing in cool, moist air, as it's entering the building, it's going to be warmed up and it's going to expand its ability to hold moisture. I know that in the Northwest, exhaust ventilation, whether it be Washington or Oregon or Northern California, that exhaust ventilation is acceptable in their codes. So, I would say that, I guess that would be my answer, is if their question is exhaust acceptable in that situation, I would say yes, by code in Washington and Oregon, it certainly is.
What kind of recommendations do you have for controls? So I know many different control features are not required under LEED. I definitely don't believe they're required under code, but I could be wrong. Definitely under LEED, if you do have controls for your ventilation, you can get extra points. But can you just briefly go over some of those?
Sure. I would say probably one of the most important controls would be a moisture sensor or a condensation control that, and again, these are, products that Panasonic makes and sells. So certainly a fan that is tied to some type of a condensation sensor that is going to trigger that fan to run, whether it be supply or exhaust, that is going to trigger that fan to run anytime you get near dew point or at that point that we talked about where the relative humidity gets high enough for the temperature of the air in the home that you might have a wetting episode. As long as that moisture is aerosolized, we don't have a problem. What we have a problem is when the temperature drops or the humidity rises to the point where we're going to have wetting episodes, condensation. So a fan that triggers to run based on condensation or based on the humidity level or dew point would be my first choice. A motion sensor is another option, whether it be in a garage to take out exhaust fumes or in a bathroom where, most of the time when someone goes in there, they're going in for two reasons. One is to create odors and one is to create moisture. So certainly triggering on motion is another good choice. But going back to the codes that we talked about, again, we want ventilation rates to be predictable and uneventful. So we can't rely on motion because if there's nobody home, and the temperature drops in the home, like in the evening or at night, we could still get to the point where we could have a wetting episode. So we can't rely on motion necessarily to trigger fans, although I think it certainly can increase the ventilation in the home. But we want to meet that ventilation code automatically, predictable and uneventfully.
All right, Jeff. Well, those are all the questions we have. We are definitely over our time a little bit, but I think it was a great conversation. So thank you for your time. Thank you all for attending. For those of you listening to this live, I have posted in several places the link to the survey. Even if you don't need CEUs, please take that link. For those of you in the future, not right now, listening to this on demand, make sure to take that 10-question quiz with an 80% passing rate to get your CEUs. Before we wrap up, Jeff, where can people contact you or find out information if they want to learn more?
As the last slide showed, they can reach me at my email address, which I'll spell out here, Jefffery, and I want to emphasize the ERY because Jeffrey is often spelled REY. So jeffernowski@us.panasonic.com. And if they have any product questions, they can always also visit our website at panasonic/ventfans.com.
All right. Thank you for your time, Jeff. Take care, everyone. Have a good rest of your week.
Thank you, Brett. Thank you to the listeners as well.